Hello and welcome to the next video of our channel Practical Hope. In this video we are going to plot Maxwell Boltzmann, Bose-Einstein and Fermi-Dirac distribution functions at different temperatures. The different distribution functions describe how particles occupy different energy levels in a system, or in other words, probability of occupancy of energy levels by the particles of a system. So first is the Maxwell Boltzmann distribution. It's a classical case. Here particles are distinguishable. There is no restriction on the number of particles in any energy state. Gas molecules follow this distribution. The expression is given by 1 upon exponential of E minus mu by kT. E is the energy, mu is the chemical potential, K is the Boltzmann constant and capital T is the absolute temperature. Next is Bose-Einstein distribution. It's a quantum case. Here particles are indistinguishable and are of zero or integral spin. An energy state can have any number of particles. These particles are called bosons. Photons follow this distribution. The expression is given by 1 upon exponential of E minus mu by kT minus 1. Finally, third case, Fermi-Dirac distribution. It's also a quantum case. In Fermi-Dirac distribution, particles are indistinguishable and have half integral spin. One energy state can be occupied by only one particle because of Pauli exclusion principle. These particles are called fermions. Electrons follow this distribution. The expression is given by 1 upon exponential of E minus mu by kT plus 1. The general expression for the three distribution functions is given by 1 upon exponential of E minus mu by kT plus A. For Maxwell Boltzmann, A is 0, for Bose-Einstein, A is minus 1, for Fermi-Dirac, A is plus 1. If we plot the three distribution functions for different values of energy, we get something like this. Here the maximum value of Fermi-Dirac distribution is 1, that is probability of occupancy is 100%. Also, it is important to note that the expression for Bose-Einstein distribution function is valid only for energies greater than the chemical potential, because for energies less than chemical potential the value of distribution function or probability of occupancy will be negative, which is not possible. The value of Bose-Einstein distribution function will be very high for very low energies. Since Pauli exclusion principle is not valid here, particles can combine to form condensates. This process is called Bose-Einstein condensation. Chemical potential is the change in the internal energy of the system when one more particle is added, keeping volume and entropy as fixed. Its value can be negative, positive or zero, depending upon the type of particles and their temperature. Here we'll take chemical potential as 0. A good understanding of the chemical potential can be found in an article by Cook and Dickerson, the link of which has been given in the description box. Let's move on to the programming part now. First, give a suitable title. Plot different distribution functions. CLC is to clear the console. Clear will clear the variables in the workspace. CLF will reset the graphic window to default values. E is the charge of an electron. K is the Boltzmann constant. U is the chemical potential and it is set to 0 as discussed earlier. Next we have to define the range of the energy in which we are going to plot the three distribution functions. So we are varying energy from minus 0.5 to 0.5 electron volts with the step size of 0.001 electron volt. Next we have to set the range of temperature. We are going to plot from 100 to 1100 Kelvin with step size of 200 Kelvin. We also need to save the name of the three distribution functions. First, set A equal to minus 1 for Bose-Einstein distribution. Later for Maxwell Boltzmann we will increase it to 0 and for Fermi-Dirac we will further increase it to plus 1. First we have to set a loop, for loop, that will vary from 1 to 3 since we have to plot three distribution functions. Then we have to set another loop J that will vary from 1 to length of T so that we can get the value of the distribution functions for different values of temperature. Finally, third loop that will vary from 1 to length of E so that we can have the values of three distribution functions for different energies. Next, write the general expression for distribution functions with AS variable. Individual rows of F matrix will have the values of distribution functions for different values of temperature. Now set A equal to A plus 1, since for Maxwell Boltzmann A should be 0. Initial value of A was minus 1, so after first increment A will be 0. For n equal to 3, we get the values of third distribution function Fermi-Dirac, since then A will be 1. Now we'll plot them. Subplot 2 comma 2 comma n. First 2 is the number of rows, second 2 is the number of columns in which we are going to divide the graphical window. N is the position of the corresponding plot. Finally, plot distribution functions for different values of energy. Set line width to 6. Set X and Y labels with font size of 6 as shown in the video. Set a suitable legend so that we get all the values of temperature. Also give a suitable title so that we get the name of the distribution function at the top along with the value of chemical potential with font size 6. So our program is complete. Let's run it. These are the three distribution functions. We have to adjust the axis. First axis 1, minimum value of xa minus 0.45. Then axis 2, minimum value of y say 0 for Maxwell Boltzmann and maximum value say 1. Minimum value of x 0 and maximum value we are keeping it as such. Finally axis 3, third chart, Bose-Einstein distribution. Minimum value of y 0, maximum value of y say 10, minimum value of x 0 and maximum value say 0.2. So these are the final curves for three distribution functions at different temperatures. Now we can also compare the three distribution functions at a fixed value of temperature. For that we need to slightly modify the program. First set a temperature say 500 Kelvin at which we are going to compare the three distribution functions. It is important to note that this value of temperature 500 Kelvin should be one of the values of the temperatures that we have already plotted. So this value of T0 is one of the values of vector capital T. Now write here if T0 equal to Tj, Q equal to J. Actually here we are saving the index of vector having values of temperature so that we can evaluate the value of distribution function for the corresponding temperature. Now this capital C will have the values of three distribution functions at the selected value of the temperature. So it will have 3 rows corresponding to the 3 distribution functions. Now we'll plot this C matrix. So subplot 2 comma 2 comma 4. 4 is the position of this plot. Plot E prime comma C prime. Line width to say 6. Since the labels are same as we used in the earlier plots, so we will copy from there and paste here. Give a suitable legend so that we will have the name of the three distribution functions as legend. Finally give a suitable title which will have the value of the temperature at which we are going to compare the three distribution functions. Font size to say 6. Let's run the program again. Go to edit, axis properties. First let's set the axis for the fourth plot. Minimum value of x say minus 0.45, minimum value of y 0, maximum value of y 1.2. We can increase the font size of the legend and set it to bold. Then set the axis for Fermi-Dirac distribution, minimum value of x to say minus 0.45. Increase the font size of the legends. Then Maxwell Boltzmann distribution, minimum value of x 0, maximum value 0.4, minimum value of y 0, maximum value of y 1. Increase the font size of the legends. Finally, Bose-Einstein distribution, minimum value of x-axis say 0, maximum value 0.2, minimum value of y 0, and maximum value of y 10. These are the final curves. So we have plotted all the three distribution functions at different temperatures, and we have also compared the three distribution functions at a particular temperature. If you like this video, share it with your friends and colleagues, and don't forget to subscribe our channel if you haven't done it yet.